Hello, my name is Kerry Mudge. I'm from the Australian Defence Science and Technology Group. In this presentation, I'll provide an overview of our current laser satellite communications program that we are undertaking in conjunction with our collaborators. Before I begin though, I would first like to thank Aerospace Corporation for organising this workshop and for the opportunity to present today. The DST Group is the lead organisation responsible for undertaking and overseeing defence science and technology development in Australia. We have an annual budget of approximately $470 million and around 2,100 staff spread across 8 sites around Australia. Recently, DST released the Defence S&T Strategy More Together, which sets the directions and establishes the overall S&T priorities for defence science and technology out to 2030. The strategy introduces a new science, technology and research, or StarShots concept, which collectively set the direction for strategic research and development into the future. Among the 8 initial StarShots, which are shown listed on the slide, is the Resilient Multi-Mission Space StarShot, which is aimed at opportunities towards providing resilient space-based services in increasingly contested operating environments. This includes a focus on secure and resilient communications delivered from space. Organisationally, the DST Laser Communications team sits within the Cyber and Electronic Warfare Division in the Protected Satellite Communications Group. PSC Group undertakes both RF and laser satellite communications R&D activities, and we are working jointly on a number of projects spanning both technology areas. The core laser communications team currently has 4 members, and though we are a small team, we work with extended teams within our own organisation, as well as a large number of external collaborations as depicted on the slide. These span Australian academia and government organisations, Australian industry and international alliances. The content of this presentation includes contributions from these partnerships. As mentioned, we have a significant number of collaborative activities that we are involved with. I would now like to present a brief overview of these activities. DST is a participant on the Responsive Space Capabilities Memorandum of Understanding, which includes membership from 11 nations, as shown. Under the RSC MOU sit a number of project arrangements, including one we are involved with, the Military Optical Satellite Communications or MOSCOM project arrangement, for which Dr. Ken Grant is the Australian representative. MOSCOM currently includes membership from 6 nations, including US, UK, Germany, Norway, Netherlands and Australia. The objectives for the PA include a focus on joint experimentation and trials, technical data sharing and harmonising optical ground station requirements. As laser SATCOM is a relatively new research direction for our team at DST, participation in these activities has afforded great benefit to our work program, in particular for the DST Small Satellite program, which I'll discuss further later in the presentation. To promote engagement within our region, DST has established a Regional Engagement Fund to support R&D collaborative activities in areas of mutual benefit. Under this scheme, we have recently had funding approved to support regional engagement between Australia with NICT and Japan to undertake enabling research activities for laser satellite communications applications. The regional proximity of Australia and Japan has evident advantages. For example, the Japanese geostationary ETS-9 mission with the Hikali laser communications payload will be visible from both countries. However, this engagement is also of benefit to Australia as we are relative newcomers to the field, and Japan has a long history with laser SATCOM being one of the pioneers of the technology. The partnering model with NICT is supported through bilateral collaborative agreements with Australian universities. The scope of activities is targeting enabling R&D on atmospheric site characterization. The 3 activities include cloud cover analysis through analysis of satellite imagery. Investigations are being undertaken by Curtin University and UWA and are based on 40 years of satellite imagery using the PATMOS-X database. The second activity is with ANU is an experimental measurement of the vertical atmospheric turbulence profile using the SkyDAR technique. This technique involves imaging a double star to probe different layers through the atmosphere. To date, this technique has been utilized at astronomical observatory sites. However, in this project, we are targeting a low altitude near sea level site, for which to our knowledge there has been very few experimental campaigns to profile the turbulence. However, these sites are likely to be important for future laser SATCOM applications, where deployment is based on other considerations such as proximity to services, etc. The final activity is to develop a numerical propagation model based on phase screen simulations. The propagation simulations utilize the split-step phase screen method to simulate the influence of turbulence on laser beam propagation. We have had a collaboration over a number of years with UWA to develop these simulation tools. Under the Regional Engagement Fund, UWA is currently adapting these simulations to run across multiple GPUs with the aim to be able to increase array sizes for long-range link simulations such as ground-to-satellite paths. These models originally were set up for horizontal propagation paths, but have been recently adapted for vertical and slant paths using the Huffenagel Valley profiles. The three simulated beam profiles show the results from a horizontal path, a downlink and an uplink propagation path for the same ground layer turbulence. In future, we will use the SkyDAR measured turbulence profiles as input to the simulations. An initiative being led by the Australian National University ANU is a proposed Australasia-wide network of optical ground stations. This network currently includes a node at the University of Western Australia, located on the west coast, the DST optical ground station centrally located on the south coast, and the ANU node located in Eastern Australia at Mount Stromlo in Canberra. There is also a fourth node proposed in New Zealand at the University of Auckland that is waiting funding outcome. The objectives for the optical ground station network are to investigate site diversity for lasercom. This is towards minimising blockages due to cloud cover and to investigate handover between sites to maximise downlink data throughput. Due to the graphical area spanned by these ground station network, it also opens up greater access to satellites due to increased visibility range and elevation to the various sites. We also anticipate future opportunities for quantum communications demonstrations through simultaneously transmitting to or from spatially separated optical ground station sites. I would like to provide a brief introduction to some of the defence-funded quantum communications activities, as there is a strong technology overlap with classical laser SATCOM. Australian research in this area has a focus on continuous variable or CV implementations. These use bright beams or coherent states such as the output from a laser rather than single photons. The quantum random states are then encoded by modulation of the quadratures of the optical field such as amplitude or phase, and on the detection side, both amplitude and phase are measured using homodyne or heterodyne detection techniques. Therefore, an advantage of CV approach is greater compatibility with telecommunications technology. Current projects funded by Australian Defence include an industry-led project through company Quintessence Labs, which specialises in both classical and quantum encryption technology. This project is aimed at maturing CVQKD for fibre and free space applications. In addition to this, there are several collaborative research projects funded with Australian universities. The project's areas include quantum repeater architectures, quantum memory development, and theoretical and experimental evaluations of CV quantum communications for satellite applications. Collectively, the total funding for these projects is 5.5 million Australian. To support the growth of the emerging space industry in Australia, a SmartSat Cooperative Research Centre was approved in late 2019. This represents the largest space industry research collaboration in Australia's history. It has a total funding of $245 million over 7 years, which includes cash contribution from government and cash and in-kind contributions from the partner organisations. To give a concept of scale, it currently has 31 industry partners, 22 research partners and 55 space startups. Defence will contribute $12 million in funding to the SmartSat over its lifetime, and as a core participant in this consortium, DST will support research projects that address Australia's need for sovereign space capabilities or explore disruptive approaches to delivering space-enabled services. The SmartSat CRC is structured into three main research themes, the first of which is advanced communications, connectivity and Internet of Things technology. A priority area under this stream is laser satellite communications. Under the SmartSat Advanced Communications Research Program, there are currently 7 approved projects that are now underway. We at DST have involvement in 3 of these, working alongside industry and academic partners. These projects include a project on coherent free space optical communications, Project Chorus, which stands for Compact Hybrid Optical RF User Segment, and a modem development project for optical and hybrid RF optical communications. I'll discuss the last 2 of these in more detail in a moment, but additional information about these and the other SmartSat funder projects can be found on the website. Project Chorus is aimed at exploring designs for integrating both laser-based and radio frequency communications into a single SATCOM user ground terminal. The project aims to take advantage of the high data rates and enhanced security promised by optical comms with the reliability of traditional RF as an opportunity to provide high availability, capacity and resilience SATCOM without requiring additional access to highly regulated and expensive radio spectrum. Phase 1 of the project is funded for $1 million over 12 months with the objective of assessing the viability of different design options. The outcome of Phase 1 is to create a virtual representation or digital twin of the chosen design to support development of a demonstration terminal in follow-on phases. The SmartSat modem project supports the development of a flexible modem architecture targeting optical and hybrid RF optical links. For Phase 1, which has been recently funded, proposed activities include development of both a software implementation suitable for COTS software-defined radios and a hardware firmware implementation targeting data rates up to 1 gigabit per second. These are to be based on a flexible design methodology and include options for gathering channel measurements and other research data. The project plans to utilise a 12-kilometre test range that extends over metropolitan Adelaide. Shown in the images below are the optical transmitter site and the optical receiver site located on a building roof at the UniSA campus. We have used this range previously with our UniSA to perform both long-term and short-term testing for RF and optical communications links, as well as channel characterization measurements. I would now like to discuss in more detail the DST Optical Ground Station Development and Small Satellite Program. We are currently undertaking the development of an optical ground station to be located at the DST site in Adelaide, South Australia. For this purpose, we initially proposed to use an existing half-metre diameter telescope that is currently employed for space situational awareness. However, due to it having some refractive optical elements, it has some limitations due to large optical losses in the near IR at laser communications wavelengths. Despite this limitation, it can still be used for some experimentation activities, and we intend to continue its use for channel scintillation measurements, turbulence characterization, and for verification of satellite tracking capability. Moving forward, we are in the process of establishing a dedicated laser comms optical ground station, which will be located about midway down the 1.5 kilometre long on-site DST laser range, about here. We plan to install a half-metre diameter telescope manufactured by PlaneWave with an L600 tracking mount, which was recently delivered to us in August this year. The terminal will be capable of dual band operation at 1064 nanometers and 1550 nanometers. The optical ground station commissioning is being assisted through a research agreement with ANU and will be augmented with an adaptive optic system and beacon lasers for uplink demonstrations. The telescope will be housed in a 6.5 metre diameter dome, which is currently under construction by Astrodome Observatories, shown here. A shipping container-based control room is already installed on site at the laser range, shown here. And the contracts for the groundworks for the dome and telescope are currently underway, and we anticipate that the optical ground station will be commissioned in preparation for on-sky tests by the end of this calendar year. DST is currently working on a small satellite project, the Buccaneer main mission. This is a follow-on from DST's first CubeSat development, which was launched in 2017. The Buccaneer mission will use a 6U CubeSat bus built by Innovor Technologies. The primary payload is a digital HF receiver to collect signals from the Jindalee Operational Radar Network, JORN, and explore techniques for calibration of this network. The JORN network is built on DST's world-leading over-the-horizon radar technology and provides 24-hour surveillance of the northern and western approaches to Australia. In addition, there are several secondary payloads, including an optical communications laser, which I'll discuss more in a moment. Other secondary payloads includes the Manoeuvrable Terrestrial and Self-Imaging System, or MANTIS, which is a deployable and retractable arm with a dual-surfaced rotatable mirror, capable of imaging both the Earth and the Beeman CubeSat itself. So the self-imaging is to verify the deployment of the 3.4 metre HF antenna. Other secondary payloads include a CubeSat radio frequency identification tag, or qubit, to aid identification during initial startup operations, and an Iridium radio for connection to the LEO Iridium constellation for routine communications. All the secondary payloads will communicate via an in-house developed FPGA and interface board. The launch is planned for early 2022 through the Space Test Program of the US Department of Defense. The LCT module for BMM is being furnished to Australia by Aerospace Corporation as a US contribution under the MOSCOM project arrangement. It consists of a 1064 nanometer laser transmitter that transmits between 2 to 4 watts of output power. The objective for the mission is downlink and uplink demonstrations using a body pointed CubeSat. To achieve this, in addition to the laser module, DST is developing a low data rate optical receiver payload, which is targeting modulation rates around 10 kHz. It has a 12mm aperture with a wide field of view to reduce pointing requirements on the satellite. UniSA is developing an optical modem for deployment on the CubeSat and the ground site for both downlink and uplink communications. This is a combined software firmware implementation with reconfigurable data rate and framing, and includes the option of an LDPC forward error correction code. Finally, I'd like to conclude by giving a brief introduction to some of the atmospheric characterization activities that we are undertaking in support of laser SATCOM. One application for atmospheric characterization studies is the optimization of adaptive optics systems. An AOS implementation is shown in the figure and consists of a wavefront sensor to measure the distorted wave input to the telescope aperture, a deformable mirror to compensate for and correct for the distortion, and then a control system to apply the correction. The output is an improved focal spot, and this is beneficial for applications such as ultra-high data rate links or quantum communications, as it can improve coupling efficiency into an optical fiber for coherent detection or for coupling onto small-sized detectors. An important parameter turbulence metric is the freed parameter or atmospheric coherence length. as this determines the limiting resolution of a telescope. It is also an important parameter for AO systems as it determines the minimum required subaperture size for correction. To experimentally characterize the atmospheric coherence length R0, we are developing a differential image motion monitor instrument. In this instrument, two subapertures with a wedge create two separate images of a single star. The differential motion of the spots can then be related to the total wavefront curvature. To enable long-term measurements, a custom DIM processing software is being developed, and the instrument will be housed in a roll-off roof observatory. As previously mentioned, the R0 can be used to characterize the local site turbulence. As our OGS site is situated at a low altitude near sea level, it has high optical turbulence. The R0 is also a useful metric for comparing turbulence at different sites. The DIM is recommended for optical turbulence characterization in the CCSDS documentation. Finally, I would like to briefly mention a lab-based optical turbulence emulator that we have been developing. This is a hardware-in-the-loop testbed used to verify the performance of optical modems and receivers. The system uses an acousto-optic modulator controlled by a custom LabVIEW program to apply synthesized statistical scintillation noise. The system currently simulates log-normal and gamma-gamma fading, but we are looking to extend this to other PDFs to simulate satellite links. So this concludes my presentation today. Thank you for listening, and I'm happy to take any questions. Thank you.